So we're doing 4.6, the natural logarithmic function. We're looking at the log rule for integration. The antiderivative of 1 over x dx is equal to natural log of absolute value of x plus c. If you recall, when we did derivatives, the derivative of natural log was 1 over x, and so logically that makes sense. If we're antideriving, it goes reverse. If u is some sort of function, we would have to do the u substitution, which is why they wrote a second rule for 1 over u, and so that would be after or during the process of doing u substitution. So we're going to start here. If I have the integral of 1 over 2x dx, I am going to let u equal 2x. Okay, we know that to be the most inner part of the function, so 1 over would be the 2x, and then the derivative of 2x is 2 dx, is a differential for du. I need it to match exactly because it's going to have to substitute in for 1 and dx. And so I'm going to divide both by 2 or multiply both by 1/2. So when I rewrite this integral, I'm going to pull that 1/2 in front of my integral, and I'll have 1 over u du. And if you go back and look, 1 over u du, the antiderivative of that is natural log of absolute value of u. So this is 1/2, keeping that natural log absolute value of u plus c. And I have to replug back in this in place of u. Unless you're doing a definite integral and you've changed your limits of integration, you do need to put your x back. And I'll have 1/2 natural log absolute value of 2x plus c. The next one is a lot like that. They've gone ahead and told us that we're going to let u equals 4x and du is 4, but again, I need it to be 1 dx, so I'm going to multiply both sides by 1/4, divide both sides by 4. So when you write this, I have 1/4 the integral of 1 over u du. We know that to be the natural log absolute value of u plus c, and don't forget the 1/4 in front. And I'll go ahead and plug my u back in. So I have 1/4 natural log absolute value of 4x minus 1 plus c. Okay, so we're finding the area of a region. If you recall, when we do area under a curve, we did a bunch of tiny rectangles, and we would do the limit as x approaches infinity, or delta x approaches infinity, which means we're getting infinitely many tiny rectangles, and we would add those all up. And we've talked about when we're adding things up or summing things up or accumulating values, it's talking about the antiderivative. The antiderivative does that for us. The antiderivative is the limit as we get infinitely many rectangles to fill in that perfect curve of whatever region we're looking for. They've told us that they're bounding the region, and so that bounded by is telling us our limits of integration one way or another. So x equals 3 is going to be one of our limits of integration. We would need to find the other limit of integration based off the x-axis. So I need to figure out where this function crosses the x-axis. I'm stopping at 3, but where else is it going to stop at? And so in order to do the x-axis, we know a function has an x-intercept whenever the function is equal to 0. Denominator being equal to 0 would be where it's undefined, but where the function is equal to 0 would be the numerator is equal to 0. And so that x-axis is telling us x equals 0. So we are solving essentially just the top. So I will do the area is going to be the antiderivative from 0 to 3 of x over x squared plus 1 equal to 0. So then I've got to think about trying to antiderive this. I can't don't go ahead and divide it because the denominator has a greater power than the numerator. And if you notice, I can't split the denominator, where if this was flipped, I could split the numerator with each denominator, but you can't do that with a denominator. And so we're going to have to probably use some form of u substitution. Well, if I just let u equal x squared plus 1, then my derivative is 2x. Okay, so let's try that. So I'm going to let u equal x squared plus 1, which is my denominator, and du is equal to 2x dx. I need it to be just x, though. And so I'm going to divide both sides by 2 or multiply both sides by 1/2. And so I'm going to have the antiderivative with 1/2 in front of it of 1 over u du However, I need new limits of integration because x is 0 and x is 3, but I have u values. Okay, so let's, we don't need to let anything. We're going to have our x that's equal to 3 and find a u that corresponds with it, and an x that's equal to 0 and find a u that corresponds with that. And I'll just plug those x values in here. Okay, so x equals 3 would be 3 squared plus 1 is 10, so that upper limit is going to be 10. And x equals 0, I'll plug it in and get 1. I'll do that. And so then I'll do this being natural log with my 1/2 in front of it, absolute value of u evaluated from 1 to 10. I don't need the plus c because it's a definite integral. I also don't need to replug back my x because I don't have any x values going on, and I don't need any x values now because I changed my limits of integration. So I don't want to put it back because then I would have done that all for nothing. Okay, these are u values. 10 is a u value, 1 is a u value. So then I can just do 1/2 natural log absolute value of 10 minus 1/2 natural log absolute value of 1, and you have to plug them back in. So I'll have 1/2 natural log of 10, and natural log of 1 is 0, so 1/2 of 0 is 0. So I just have this, which is approximately 1.15129, because we could actually take those absolute values. This next one, I can't just let u equal the denominator because I would have x squared plus 1, and then my derivative would be 2x, and that doesn't satisfy plugging into the top because I have an x squared in the top. Since the degree on top and bottom match, we can actually do the division of it. It's something we can actually divide by hand. And so we're going to have to review a little bit of long division here. So I'll do x squared plus 0x, we need a placeholder there, plus 1. And see how that goes into x squared plus x plus 1. So you have to ask yourself, what am I going to multiply this x squared by to get this number? And the answer to that is 1. And so I'll have 1 times x squared, you got to distribute it, is x squared. 1 times 0x is 0x. 1 times 1 is 1. And then you have to subtract that entire thing so that I get this cancels. X squared minus x squared is 0. X, and this becomes 0 too. So then I can't make x squared into x. There's nothing to multiply x squared by to get to x. And so that's your remainder. And just like you do with numbers, your remainder is that value over what you were dividing by. So I have this. So I am now integrating 1 plus x over x squared plus 1 dx. It's important to put those parentheses around it because the entire thing has the integral and the entire thing has a dx. Okay, well, we can actually integrate this in pieces. I can integrate the 1 dx, and I can integrate the x over x squared plus 1 dx. So the first one, it's easy, so I'll hold that thought. But over here, I'm going to have to do u substitution. I'm going to let x equal, or u equal x squared plus 1, so that du is equal to x dx. Of course, I need it to just be x dx, so I'm going to half both sides or divide both sides by 2, so that I have 1/2 the antiderivative of 1 over u du, which is 1/2 natural log absolute value of u plus c, which is 1/2 natural log absolute value, plug my u back in, x squared plus 1 plus c. And then if I bring down this, the antiderivative of 1 is just x. And then we would have our plus c, and those plus c's would combine to begin a different constant. And so we would have just that. And you can actually drop, if you wanted to, you could drop those absolute value bars because it's impossible for x squared to be negative, and then you're adding 1, so it's still impossible for it to be negative. So you can only take natural logs of positive numbers or 0. And so this could be written like this because it's impossible for the absolute value loses its value or its importance at that point because it's impossible for that to be negative, and so the absolute value is not needed. Okay. But you can leave it as well. All right, so here's another one that we're going to do. All right, so if we let x be the denominator, we would end up having to chain rule it. And so we would have x plus 1, and then we'd have 2 in the front of it, and then you're end up with a plus 1. And I can't, if you notice when we're trying to make things match, we're dividing both sides or multiplying both sides by something. We're not adding or subtracting because we can't do that when they have the dx attached to a multiplication. We can't put a plus inside of a multiplication. And so that won't work. So what we're going to do, instead of letting it equal the entire denominator, I'm going to let u equal part of the denominator. And that makes du equal to just dx. So I'm substituting in here, and I still don't have anything to substitute in for up here. But what I can do is I can actually find something to substitute in for x by solving this. I'll just subtract 1 from both sides so that x is equal to u minus 1. So then when I go to plug in everything, I'm going to pull that 2 out front. It'll be a little easier so that the top, it'd be like doing this, is just x. And in place of that x, I'm going to have u minus 1. And in place of the x plus 1 on bottom, I'm just going to have u. And then in place of that dx, I have just du. So everything here. And it doesn't necessarily look like we've done anything, but we have, because before we couldn't actually do that division because the denominator is greater than the numerator. And we can't split the denominator into a sum. Even if you were to distribute that out, you can't split the denominator, but you can split a numerator. And so because of what we've done, I can rewrite this as u divided by u squared, which is 1 over u, and negative 1 over u squared du. So I'll have that too. The antiderivative of 1 over u is natural log absolute value of u. And then keep in mind this term right here is like this. So if I increase the power by 1, I have a negative 1, and divide by that value, I have negative 1 over u to the negative 1, and that u to the negative 1, I'll move back down. So I'll have this plus c. And then you're not going to leave it like that. We're going to have to actually plug in our x value. So we have equal to natural log. And I'm going to distribute that 2 in the same process so that it doesn't look so choppy, I guess, with the plus c. You could leave it outside. So my u is x plus 1. And I have 1 over x plus 1 plus c. And I almost forgot to distribute that 2. And I'll put that 2 there. And I think that looks a little bit nicer. But if you wanted to leave the 2 outside the parentheses, that would be fine. You would just have to plug in the x plus 1 either way. Okay. All right, so we have this solving the differential equation here, and we have a product in the denominator. And when it says to solve a differential equation, that means you're going to end up with a y equals. That's your goal. Okay, so what we first want to do is we want to think of it as a differential. So I like to rewrite it, dy equals 1 over x, natural log of x, and multiply both sides by x, dx. So it's got that differential that we learned how to do. And then in order to solve the differential equation, I'm going to integrate both sides because the antiderivative of dy is y equals, and we need a y equals so we can get an equation. And then I'm going to have to do a little bit of work on the right-hand side. So the left-hand side is pretty easy, but the right-hand side is going to require more work. So what I'm going to do is I'm going to let u equal natural log of x. So that's substituting in just this part here. But what's great about that is du, the derivative of natural log of x, is 1 over x dx when written as a differential, which substitutes in everything. Okay, so I'll have y is equal to the integral of 1 over u du. So it doesn't look like it's going to plug in, but if you think about when we have a natural log in the denominator, the derivative of a natural log is 1 over x, and so it substitutes that in wonderfully. And so I'll go ahead and simplify. So y is equal to natural log absolute value of u plus c. And then I'll need to plug in my u. So it's a little weird looking in the sense that our answer is y equals natural log absolute value of natural log of x plus c. And that is your answer. So let's bring in some trig. We haven't done any trig in a little while. And so I think this would be useful unless you just have the antiderivative of tangent memorized. None of our derivatives that we had memorized had a derivative of tangent, like the result being tangent. It was something always with tangent. And so we can't reverse that. As if I said, what is the antiderivative of cosine? You would know it was sine. We can't do that with tangent. We didn't memorize one where the actual output of a derivative was tangent. But what we can do is let's rewrite that and think of it as tangent being sine over cosine. And then we can let u equal the denominator so that du is cosine x. Oops, sorry, not cosine. Sine x. The derivative of cosine is sine x dx, which if you notice, there's my u and there's my du. So when I go plug this in, I am doing the antiderivative of 1 over u du. Okay, because I replace the sine x dx with 1 du, and then I replace the cosine x with just u. And so this is equal to the natural log absolute value of u plus c, which is equal to the natural log absolute value of cosine x when I plug my u back in, which leads me to these, which could be useful to memorize, which we've already talked about this one and this one in a memorization. But the others we haven't, because they require natural logs, and at this point we hadn't worked with natural logs very much. We've done derivatives of them, but we hadn't done antiderivatives of them. So tangent is the antiderivative. Oh, I made a mistake. That reminded me. The derivative of cosine is negative sine. So we would have had to negative to change it. And that changed a little bit of everything. Very important. So sorry about that. I caught that by looking here. So it's important to have somewhere to check ourselves. And so it's negative natural log cosine. And then if you do cotangent, it's positive of sine. And then secant still goes with secant. Tangent must no longer multiply. We do derivatives of secant. We get secant tangent, but that's not the case whenever you're going to do the antiderivative. And so it might be helpful to have this easily accessible to a reference, especially while you're doing your homework. It is in your textbook if you just go back a couple pages and working on your homework. But it'd also be helpful to memorize, especially these three. Okay, those would be your most common ones that are used, but the other ones will show up from time to time. Okay. All right, so then we have this. We're going to be using our trig functions here. And it's a definite integral, so we are going to have to plug in 0. We are going to plug in pi over 4. So our unit circle is going to come in handy. So what we want to do is be able to rewrite it in a way that we want. There's no rule that we've used so far in calculus yet that we can substitute in, like let u equal 1 plus tangent squared over x or of x. I still don't have anything to do with that, or if we do the derivative of that, it's not going to work out. But what does work out is we can actually use an identity from pre-calculus. So I'm sure you all remember this identity here. It's a very common one. Sine squared x plus cosine squared x is equal to 1. What's fun about that is if I'm working with tangent, I can make that into a tangent. Okay, so if I'm trying to get tangent, that's sine over cosine. I'm going to intentionally divide every term by cosine squared x, so that I get tangent squared x, and I simplify that first term. Cosine squared x plus cosine squared x is 1, is equal to 1 over cosine squared x is secant squared x. Okay, and if I were to square root both sides, it's just secant. I get the square root of, and for the sake of what we're trying to substitute in for, I'm going to use the commutative property and rearrange my 1 plus tangent squared x from being the tangent squared x plus 1. And keep in mind, secant squared x is the same thing as secant x, all being squared. So I square both sides. Now look at that. That matches. This actually is a trig identity. It's just probably not one that you would remember as well as the sine squared plus cosine squared equals 1. So now I can substitute in, and everything's still x, so I don't have to find new limits of integration at this time. So I have 0 pi over 4, and then I'm replacing that root 1 plus tangent squared x with secant x dx. Almost forgot. Okay. And then what's great about that is if you go back to the slide we were just on, it told us that the antiderivative of secant x was secant x plus tangent x. So this is equal to the natural log absolute value of secant x plus tangent x from 0 to pi over 4. We've got those absolute value bars for a reason. So then here's where our unit circle comes into play. So if I have a circle, we'll do a nice circle for once. Okay. And we are looking at it here. And we're looking at just 0 and pi over 4. And if you keep in mind that secant is 1 over cosine, just keep that in mind. I'm going to write it down here as a reminder. And keep in mind that this is sine over cosine. Okay? That'll be helpful when we're doing this. So we're looking at pi over 4, which has the ordered pair of root 2 over 2, comma, root 2 over 2. And then we're also looking at 0, which has the ordered pair 1, comma, 0. And keep in mind also it's cosine, comma, sine. So cosine is the x value of each ordered pair. Okay, so if I am doing this, I will have, plugging in these values, I'll keep this in a little bubble. That was a little side note to help us out. We have the natural log absolute value. When I do 1 over cosine of plugging in pi over 4, because you plug in top minus plug in bottom, I'm going to have 1 over root 2 over 2. Okay, now just another little side bubble, 1 over root 2 over 2. You multiply by the reciprocal, you get 2 over root 2. If I multiply top and bottom by root 2 so that I can rationalize it, I'm going to end up with 2 root 2 over 2, which is just root 2. So 1 over cosine x is just root 2 for pi over 4. That was all for secant. Now for tangent, it's sine over cosine. And so sine is root 2 over 2, and cosine is root 2 over 2. So same thing over same thing is 1. So I'll have plus 1. Okay, so I have that, absolute, which is great. So absolute value bars aren't super needed right now because root 2 is positive and plus 1 is positive. But since I already wrote them, we'll just leave them. Minus, then, plug in the bottom number. So secant of 0, okay, is 1 over cosine. And cosine is the x value, so 1 over 1 is just 1. Minus, and then we're doing sine over cosine, still at 0. Okay, because remember, this was our pi over 4. This is 0. And that is 0 over 1, which is 0. Okay, and natural log of 1 minus 0 is natural log of 1, and natural log of 1 is 0. So that whole term is 0. So if you're looking for an exact answer, it'd be this. If you are looking for a decimal approximation, it is 0.88137. So unit circle, don't forget it. We will at some point be reviewing that heavily before your AP test. All right, last thing is when I talk about average value, I'm not sure we talked about it before. If you think about averaging things, you're adding up things and you're dividing by how many things you're adding, but we're adding up infinitely many things. So when we're doing our average, we're going to divide by the distance between our limits of integration, our x values. Okay, so like if I'm going from 0 to 2, I'm going to divide by 2. If I'm going from 3 to 9, the difference between those numbers is 6, I'm going to divide by 6. And so when I do this, the way to get that is you're always these limits of integration. If you'll just subtract the bigger one from the smaller one, or smaller one from the bigger one, that's what you're going to multiply by to get that distance. Okay, if you think about how far away those are, they're pi of 4 away from each other, and that's what I'm dividing by. Instead of writing as division, though, I'm going to write it as a multiplying by a fraction. Okay, my limits of integration are from 0 to pi over 4. They gave us that. And you're doing the average. And again, remember, the integral is adding up a bunch of things, and that's why we're dividing by how far away they are or how far the endpoints are from each other. And we're doing the antiderivative tangent x dx. So this is the average value. So if you're doing average value, you're going to do 1 over b minus a times your integral from a to b of your function dx. And when I say b minus a, that is average value for f of x on a to b. Okay, that's in your textbook, and it shows up multiple times. If you're asked for average value, you're just doing the integral. You're finding the total value or total area, and then you're going to be multiplying it by 1 over the difference of your limits of integration. So I'm going to keep my fraction here for now. And the antiderivative of tangent x is the one we just found, if you remember that. And that was natural log absolute value negative. Let's put that negative out front. Cosine x. And we don't need the plus c. Almost wrote it out of habit because we're going to evaluate it from 0 to pi over 4. Okay, so then now all we have to do is plug in that pi over 4 and plug in 0. And so that unit circle we just used, I can just scoot over and we'll use it. So I'm going to equal this. Instead of writing this that way, I'm going to write it as negative 4 over pi because we can just multiply by the reciprocal instead of dividing by a fraction. And then I'll have natural log absolute value and cosine of pi over 4. If I go back over here, cosine is the x value, so root 2 over 2, which is a positive number. That looks like a 0. So you wouldn't have to write the absolute value bars. And then minus negative 4 over pi. Because I'm minusing negative, I'm writing it as a positive. Natural log absolute value of cosine of 0. So again, if I go back over to my unit circle, cosine of 0 is 1. So I have this. Reminder, though, that natural log of 1 is 0, which means 4 over pi times 0 is 0. That whole term is going to be 0. And I'm left with negative 4 over pi, natural log absolute value, root 2 over 2, which is approximately 0.44127.